All right. Okay, so welcome everybody again. Today we will be addressing Hartree-Fock theory. So last week we've been talking about an introduction to theoretical molecular physics. We have learned about the Heitler-London and the Hund-Malikan-Bloch approach. And I said that we're going to extend this point of view. We will be using a linear combination of atomic orbitals to obtain molecular orbitals, and we will build our n-electron wave function from these orbitals. And Hartree-Fock theory is a theory that allows us to derive a set of orbitals in a minimization procedure. So we are looking for the electronic state, which is the lowest possible electronic state of a given molecule. Okay, so doesn't do what I wanted to do. Let's try it this way. You can still see the slide. Okay, perfect. Right. Okay, so Hartree-Fock. First, we have to clarify the concept of molecular orbitals. Well, I said last time that atomic orbitals are the eigenfunctions that we have when we have an electron in the Coulomb field of a nucleus, and we can solve this analytically because of the high symmetry. And you are familiar with the solution of the stationary Schrödinger equation. You get the wave function, which has this radial part and the angular part. The angular part gives rise to this, or is representative of the conserved quantity of the angular momentum. So we have S, P, D, and so on as these orbital shapes. And we have a certain modulation also in the radial part, according to the Laguerre polynomials, which appear as the solutions of the radial part of the Schrödinger equation. Okay, so that's solved. We will use these results for the atom to build our molecular orbitals. But in contrast to atomic orbitals, molecular orbitals are our sort of invention. We take this idea that the molecular orbital can only be occupied by 2 electrons from the atomic orbital concept. So we say a molecular orbital is an orbital that spreads out over the entire molecule, and it is capable of hosting 2 electrons, which have then to be of different spins, so spin up or spin down. We will distinguish between orbitals and orbitals, spin orbitals, spatial orbitals. Okay, so a spin orbital is by definition then an orbital that can only be occupied by a single electron, because it also contains the specification of spin already. Okay, so that's what we call a spin orbital, in contrast to a spatial orbital, which just describes the probability of finding the single electron somewhere in space. So it's this, it is the spatial part of the one electron wave function that we think of as the orbital. And so in order to get to the spin orbital, we would have to multiply this spatial part with the spin function, either spin up and spin down. So here on the slide, you can see we're going to define this set of orthonormal functions, spatial functions, which are written here as lower caps psi. Okay, so these are spatial functions, and they form an orthonormal set. So this gives us a delta ij, and in principle any function, if this is a complete set, could be expanded in this basis of orbitals psi, right? Now we just do one more extension. As I said, we take this spatial part psi and multiply it with a spin function, either alpha or beta, denoting up and down. So you see there is this omega, so alpha of omega and beta of omega just denotes that that spin degree. We have to give it some internal variable to say it's either spin up or spin down, either alpha or beta. And so since the spatial functions are orthonormal, so is this product of the spin functions as well. So we can write this as integral over x chi times chi j, and we will use this convenient notation introduced by Dirac. So this is a scalar product with a dual basis vector coming from the left, chi I times chi j, giving us delta ij. Okay, so this is where we start from, and now comes the idea of extending this to a whole bunch of electrons. So we say that we can put one single electron into a spin orbital. Okay, now we have n electrons because we have some molecule with 16 electrons, for example. We have to get them all into a total wave function description now, which fulfills certain criteria. We already know which criteria have to be fulfilled because it is a fermionic group, or it's a fermionic particle, so it has to be an antisymmetric wave function in total. So now I'm writing a uppercase psi here as the total electronic wave function. And just as a reminder, psi here is the total electronic wave function. So it's only describing the positions of the electrons in space. So the electronic density distribution, if you take the square of this value, the square of psi, okay? And note that we writing here an x1, x2, and so on till xn. Here I'm following the nomenclature of the book of Szabo and Ostlund. So most of this slide's content here in the next few minutes is taken from this book of Szabo and Ostlund. You can get it at the Dover publisher. The Dover Publishing House is known for producing super cheap books because they are not typesetting them again. They're just basically scanning books where they have gotten the rights, and then they just reproduce it as they were, which keeps the costs lower. So I think this book, if you're interested, costs something like 15 euros or so. You can find it online. So I have the important chapters already condensed, and they are available at the Teach Center, but I can recommend it because it's a very small investment and it pays off because it's probably, although it's already an old book, the most profound introduction to Hartree-Fock theory. It's covering Hartree-Fock on 100 pages. Okay, so using this nomenclature, we are writing now x1 and x2, denoting the combined spatial coordinates of electron 1 plus its spin. Okay, so this is a convention of Szabo and Ostlund. If they speak of R, as lower caps R, R1, R2, and so on, then it is the explicit spatial coordinate of the electron 1, 2, 3, and so on. And if they write it as an X in this bold type font, they indicated it is R plus omega. So it is R and also the spin coordinate in it. Okay, so these are our n electrons. And in order to get this antisymmetric total electron wave function, we fall back on the Slater determinant idea. We have learned about this last time. So we can write now an n by n matrix and take this determinant to have automatically a n electron wave function, which fulfills all the criteria, namely it changes its sign if we exchange two electrons. Because if you look at the determinant as it's written here, exchanging two electrons would mean to change two rows of the matrix, right? And if you change two rows, it picks up a minus sign. The determinant picks up a minus sign. Okay, so this is how we get the antisymmetric n electron wave function. You see, this is a long, depending on how many electrons you have, it's a long product, a sum of product functions with alternating signs, because this is what you get when you calculate the determinant of this matrix. And to keep things simple, we will fall back on the shorthand notation as it's shown here on this slide. So I'm just writing this as a ket vector here, and I'm only using the diagonal entries of the matrix to identify the state. So it's chi I, chi j, and so on till chi n in the end. Yeah, it should be an n actually here in the ket vector. So that's how we are going to refer to the state, but keep in mind that it is an anti-symmetrized product, right? So it's not just the single product, but also all these other terms that we need in order to end up with a wave function for these n electrons that shows the correct behavior. And now we come to the big question. Well, okay, here we have now constructed the n electron wave function under the assumption that we already know how these orbitals chi1 to n look like, right? So if we have these n orbitals, then we know how to build the wave function. That is the easy part. The question is, how do we get to the actual orbitals chi1 to chi n needed to construct the n electron wave function? And the idea is that we're going to obtain this from a variational method. We are trying to minimize the electronic energy. So if you take the electronic Hamiltonian, here written as H in this math font, and we calculate the expectation value in this state, n electron state, which we consider the ground state. So we write it as uppercase psi naught. Okay, so this is the lowest electronic energy state the system can be in. And so it is the expectation value of the Hamiltonian when sandwiched from left and right with this wave function psi naught. Okay, so this would be the energy. And now what we're doing is we say, okay, we are offering a certain variation in the wave function psi naught. So we are going to vary this wave function in such a way that we obtain a minimum for the electronic energy E naught. And as you will see in the next hour, this minimization will lead to a set of equations for these orbitals. And this set of equations looks like the equation that's written here in the middle of the slide. Fi acting on chi of electron I gives us back this orbital multiplied by epsilon. So it is an eigen value problem that needs to be solved, and the corresponding operator on the left-hand side, this F, is the so-called Fock operator. Okay, so these are the Hartree-Fock equations in a molecular basis. They look pretty simple, and the Fock operator itself is written on the last slide, on the last line here on this slide. F of I contains in principle expressions that refer to the kinetic energy of the electron in this orbital. You can see nabla squared. This is the kinetic remains of the kinetic energy expression. And then we have two terms. One is simply the Coulomb interaction of electron I with nucleus A, plus, and then a term which is denoted here as the so-called Hartree-Fock potential. This is the potential felt by the electron I in the field of all the other remaining electrons in the system. So this is why the Hartree-Fock method is called the mean field theory, because we will we basically solve for each orbital, assuming that each orbital, when occupied by a single electron, is created through the desire of this electron to have a configuration that works out with the Coulomb field of the nucleus and all the other electrons in an averaged state, right? So you take all the electrons, the remaining electrons, and they create a certain field environment. And in this field environment and in the environment of the actual nuclei of your molecular system, you are having this electronic wave function for the single ith electron that you are looking at. Okay, so this is the idea. So
can I quickly ask something?
mhm.
Why don't you refer to the F as H like the Hamiltonian? Isn't that just the expression for the energy that
Yeah,
you would
this is
also have in a Hamiltonian?
mhm. That's a good question, but yeah, and I'm glad that you asked, because the Fock operator is not an operator that gives you the energy. Okay, so it's not the energy. You will see in a minute, because what we are doing is, when we apply the variational method, you have an expression for the energy as it's written here, but you would try to minimize with respect to a variation in your orbitals, right? So you take the derivative with respect to some parameters which describe your wave function, and you would like to find those parameters. So it's like a test function which you vary, and you try to find those parameters for which this expectation value is lowest. So this operator appears only in this derivative process, when you take the derivative with respect to the parameters. And there is another thing that comes in. We are doing an optimization with a constraint. So how would you handle a optimization with a constraint typically? What would be your mathematical approach to it?
Lagrange multiplicators?
Exactly, yes. And so that's what's going to happen on the next slide. Or maybe the next. Okay. It's coming up, but we will have to introduce the constraint that we would like to keep the molecular orbitals orthonormal at all times. So this will be our constraint. But before getting there, I realize I have another slide, which is just showing you the actual energy that corresponds to a given electronic state. Because basically, before we start now Hartree-Fock and take the derivative with respect to these internal parameters of the wave function that we are seeing as a test function, right, and which we want to optimize to give the lowest energy, we first think about how does the actual energy look like. So if I have a given n electronic wave function, and so all the orbitals are known, how would the energy itself look like? Right? So that's important, because we will use this information later on when we do the actual variation. Okay, so this is something that we will be discussing first. Let me just check. Yes, okay, so that's what's coming up on the next few slides. So this is our Hamiltonian. You can see, for example, in the case of the H2 system, we have two nuclei, we have two electrons. And so we have a kinetic energy operator for each of these electrons. We have a Coulomb interaction of each electron with the nuclei. And we have an electron-electron interaction term, which is denoted here as 1/R12. You might also note that we have switched to atomic units here, because there is no constant in the picture anymore, right? So everything has been set to 1. Automatically, this means that our energy will be now in units of Hartree, as we discussed. Just a reminder, Hartree is a big energy unit. 1 Hartree is 27.2 eV, so it's exactly double the value of the so-called Rydberg constant. If you remember the ionization energy of the hydrogen atom, 13.6 electron volt. So that's the unit we will be working with here. Okay, so this is our Hamiltonian. And now, in order to find out how the energy really looks like in the case of a n-electron wave function being built from molecular orbitals, we are sandwiching it now. Okay, so Hartree-Fock, the Hamiltonian is now sandwiched from left and right with our antisymmetric n-electron wave function. And that's what we have to calculate now quickly. So in order to do that, we will split the ingredients in the Hamiltonian into several contributions. And let me go back one more time. So the way how it's written here on slide 119 is already grouped with a certain meaning, because this first bracket expression here is basically the first electron interacting with both nuclei and its corresponding kinetic energy. And the second bracket term is the second electron interacting with both nuclei and its kinetic energy. So these terms are called the so-called core Hamiltonian expressions. This is a one electron term because it's only relevant for a single electron. So this part of the Hamiltonian depends only on one specific electron coordinate because it's this part for this electron and then another one for the second electron and so on. And then you have this term 1 over R12. And this is something we are going to call the two electron term because it will couple the motion of two electrons. It is the part of the Hamiltonian that depends on two electrons at the same time. Okay, so these are the ingredients we're going to work with now. And let's start now with the core Hamiltonian parts and look at the expectation value for our antisymmetrized two electron wave function. We have hydrogen 2, so we have two electrons in the system, and we can easily write our actual wave function now explicitly as the determinant. So we evaluate the determinant and we obtain this expression. You see you have two terms because what you do is it's a 2 by 2 matrix. So you take product of the diagonals minus the product of the anti-diagonal. This gives you your determinant. Then you come in from the left. This gives you complex conjugate, therefore the star here notation. And you come in from the right with the same type of wave function because we're sandwiching the Hamiltonian, the core Hamiltonian here from the left and from the right with the same ground state wave function psi naught. So that's what's done here, and then we multiply the terms. And now you can see something very convenient because if you look at the actual operator H, R1, H, R1, H, R1 every time, but this means that the operator is not a function of the second electron coordinate, and immediately we see that if we integrate now if we integrate the first electron coordinate, we won't get a result because we don't know chi1. So we would need to know the orbitals to evaluate this, right? So this is an integral that we would have to evaluate numerically. But what about the other part, namely the integral over the second electron coordinate? In this case, the operator itself does not depend on it. So it's a direct meeting of the second electron part coming from the left with the second electron part coming from the right. And now we remember that we have chosen orthonormal orbitals, and this means that when looking at the second electron coordinate, if we come in with different orbitals from left and right, these expressions will be 0. So after integration over x2, these two terms here are 0, because you can see in the second electron coordinate, for example here, we have a electron coming from the left in orbital chi2 and on the right in orbital chi1, right? So this is a direct mix of two, direct product of two orbitals. We integrate over it. We know that they are orthonormal, giving us 0. Remember the delta ij we discussed before. So we can do this now for H1. And we can do this also for H2. And since we realize that the operators that we have looked at before, see this operator here and this operator here, they are identical except for the fact that one refers to electron 1 and the other one to electron 2. So it's the same operator that appears for the different electrons. So what we see here is that in our case of a determinant built for 2 electrons, we get an expectation value for this core Hamiltonian as an integral over our core Hamiltonian for the first orbital and an integral over the core Hamiltonian for the second orbital. That's all that's left. And you can extend this to an n electron problem. In the case of n electrons, you would simply have a sum over all your orbitals. So sum over n, nhn, right? Or probably better say it this way, sum over I equals 1 to n, IHI, right? So you just have to sum over these types of integrals. So here we have used this Dirac notation again in an abbreviation for H, because we know this is the same single electron or core Hamiltonian operator for each electron. And we can refer to the ith orbital now in a shorter version just by the number, because it doesn't matter if there is now a chi written here or if we just write the number of this orbital chi, right? So chi 1 is 1, chi 4 is 4, and so on. So this is a convenient shortcut notation of these integrals that appear here when calculating the expectation value for the core Hamiltonian. I have used a slightly different symbol here for the operator. I'm denoting this as O1. Why? Because the actual core Hamiltonian in our n-electron Hamiltonian is a sum expression of all these core Hamiltonians for each electron. So in the case of 2 electrons, we have 2 of these core Hamiltonians. If I have n electrons, I have n of these core Hamiltonians. And so I will just write this sum over these core Hamiltonians as a 1 electron operator, just in general. So any type of 1 or single electron operator will lead to an expression that looks like this: a sum over integrals for each of the orbitals that are occupied with electrons, and these orbitals sandwiching our core Hamiltonian, this 1 electron term. That's the evaluation of the first part. And now we come to the 2 electron part. So also to generalize, I'm referring to this type of the operator of the Hamiltonian as a 2 electron term. Fortunately, in electronic structure theory, we only have to worry about this 2 electron term. There's only one. It's the Coulomb interaction between the two electrons, between 2 electrons. And so if we look at our situation again for the hydrogen 2 molecule, we just do the same thing we did on the previous slide. We are sandwiching now our operator from left and right with our anti-symmetrized product. Now the operator itself has the form 1 over R12, which indicates that it is a function of 2 electron coordinates, of the first and of the second electron, because R12 is R1 minus R2 absolute, right? So this is the distance between the 2 electrons somewhere in space. And I multiply it out like I did before. Unfortunately, here I can no longer fall back on orthonormal relations, because our operator is an operator that depends on both electron coordinates, right? So I can't pull over any of these functions and execute the integration directly, because this operator is a function of both variables, right? So I have to evaluate these integrals. But we can see that the first and the second terms are equivalent, and so are the third and the fourth, because in the 1 over R12, it doesn't matter if it's R1 minus R2 or R2 minus R1, so the operator doesn't change. So if you change the positions, so let's see what's these first 2 terms. In this case, it's the 1 over R12 term, and we have products of first electron in orbital chi1 meeting first electron in the same orbital. and second electron in Chi2 meeting itself in the same orbital. So it is, we could rewrite this as Chi1 absolute square times Chi2 absolute square multiplied by 1 over R12, and this whole expression integrated over 1 over x1 and x2. So this would be a simple Coulomb interaction of two continuous charge distributions in space, because each of these squared wave functions would be something like the electron density distribution for an electron in this orbital. Remember, psi squared gives us the probability. So this has a classical interpretation that would be the simple Coulomb type interaction. And due to our normalization of the determinant, we have this factor 1/2. But since these two terms are identical, it gives us 1/2 plus 1/2 giving 1, the first expression here. And we have the two remaining terms, the third and the fourth term. Here, if you look at what's going on, it's again the operator 1 over R1, R2. But here, if you look at the first electron, denoted by x1, it is sitting in orbital 2 on the right side, but it is sitting in orbital 1 on the left side, right? So this is now this fancy mix that stems from our anti-symmetrization request. It's no longer something that I can interpret as a probability, as a density distribution, because it is a product of two different wave functions of Chi1 and Chi2. So this is what we call the exchange integral. And it occurs twice. The third and the fourth term are identical, so we can collect them, put them together, and obtain this expression as shown here. And again, we make a shortcut. We are going to write this as follows. We write this as, in our bracket notation, as 1, 2, 1, 2 minus 1, 2, 2, 1. So we have only, we are kind of referring to the orbitals through these numbers, meaning from the left, electron 1 in orbital 1, orbital 2 in orbital 2, and from the right, first electron in orbital 1, second electron in orbital 2. Okay, so this is the shortcut, and you might also wonder, I mean, wait, this looks like a scalar product. Where has our operator disappeared to? And this is just a convention in electronic structure theory that you don't write the 1 over R operator, because it's obvious from the shape then. So if you use this bracket notation, there is no operator, and it's this type of 2 electron integrals, it is obvious that it's the 1 over R, the Coulomb interaction between two electrons. I have summarized this here, this convention or this nomenclature thing. So in general, if I have this type of integral where I'm having first electron in some orbital I, second electron in some orbital j from the left, and on the right-hand side, I have the first orbital in some orbital k, and the second electron in some orbital L. I will simply write this as IJKL. So the only thing that remains is the actual indices of the orbitals that are involved. And the electron index is obvious from the bracket notation, right? The first is the first, the second is the second electron. And then on the right-hand side, the first is the first, the second is the second electron. As if this wasn't already like abbreviated enough, there's another shorthand notation that you might find in articles or in books on electronic structure theory, because exchange and Coulomb terms are always appearing together due to the fact that this is how we built our antisymmetric wave function. If we multiply this out, we always have these direct terms and the cross terms, right? So it is a convention to compile these two things, the Coulomb integrals and the exchange integrals, into this double bar notation here, right? So if there's this double bar in between, it just means it's the Coulomb integral and then also the exchange integral. If you look at how this looks like in terms of positions of the indices, you just have at first for the Coulomb, you have Ij meeting Kl. And then if you look at the exchange, you have Ij meeting Lk, right? So you had this swap in the indices on the right-hand side. This gives you automatically then this corresponding exchange or Austausch integral that belongs as a partner to its Coulomb integral that we had here before.
I have a question
Yes.
about that. Is it really still a Coulomb integral even if I does not equal K and J does not equal L? Because I would suppose that it's only if two identical ones meet, then their product gives the...
Yes, is correct. Yeah, you're right. Because we will encounter situations where these orbitals, so here we are working with molecular orbitals, but we will build these molecular orbitals from atomic orbitals, and these orbitals can be even located at different atoms, right? So this is a product then of functions that are located at different atoms, and so in this case it would be even further away from this classical picture of having a real electron density distribution. Yeah, thank you for that. Okay, right. One way of writing this in the integral notation is also introducing the permutation operator, because I can say this combination of ijkl minus ijlk is the same thing as saying, and now I take ijkl, the correct order that corresponds to this type of integral. In the middle, the operator 1 over R12. And then, so this 1 is covering this part. And P12 is an operator that acts on the right-hand side and exchanges the positions of electrons 1 and 2. It swaps, or it makes electrons 1 and 2 swap places. So in this case, then electron 2 will be in K and electron 1 will be in L. And so this permutation operator then gives you exactly the second term. For those of you who are going into more detailed of many particle physics, the whole thing that I'm talking here and which we are working our way through like explicitly in a set of spatial basis functions, because this is actually what we're doing. We are looking at these abstract quantum mechanical state vectors in the space of electron and electron spatial coordinates and spin coordinates, and integrate this out explicitly. It's also possible to do this all formally within a quantum mechanics notation that uses second quantization, introducing an creation and annihilation operator, and do the same maths that we're doing here explicitly in the spatial representation in a more abstract way. Okay, so I'm just saying this. Some people find it easier. It's more abstract, and but you can exploit a lot of features of linear algebra that you learned before. But here we're going to deal with it in this spatial wave function based perspective. So we have this continuous basis that we introduce. So to make this link to quantum mechanics, all these pictures that Szabo and Ostlund mix, like saying, okay, this is how it looks in the Dirac picture, and this is the explicit integral, is actually something that we would obtain as physicists by pushing in a continuous basis the 1 in the spatial basis of the electron 1 and then of electron 2, right? This gives you then your integrals, and you can translate if x is coming from the left and hitting a wave function or a state vector, then this gives you its corresponding wave function, right? So this is a very free and probably not so refined, but very effective way how this is handled in the book of Sauer and Ostlund. But for you as physicists, you know the background of Dirac theory and the method itself. So just to make this link, this what we see here is what you get when you introduce a continuous basis and represent the whole state in this basis of electron coordinates. We have a couple of relations. IJKL is equal to JILK. Well, this is obvious because we know first electron here meets first electron here. So this would be integral IK and integral JL. And the same here, JLIK doesn't change anything in the final outcome. Then since it is this scalar product of the state vector with its dual space vector, it also fulfills this constraint that if you take, if you do this transpose and the conjugate, it is identically. And this expression, maybe someone can explain to me what's going on here. IJKK is equal to 0. How came?
And then the Coulomb part is equal to the exchange part.
Exactly, yeah. I'm just checking if you still have the attention, but this is the perfectly correct answer. You just have to notice that this is the double bond notation we introduced before, right? So, and if K is the orbital for the first and the second electron on the right-hand side, exchange and Coulomb term, or this crossover terms and the direct terms will be identical, and therefore this term would vanish. Okay, nice. So here we go. Just to confuse you a little more, unfortunately, there are other notations in books. And so this stems from the fact that chemists and physicists approached this slightly differently, and chemists were less familiar with this Dirac notation. And in some cases, it even makes sense to swap to something which is called the chemist's notation. It is written in this this bracket notation with rectangular brackets, so this square-shaped bracket here, IHJ. This is identical to our Dirac notation before. But for the 2 electron integrals, it is different, because in the chemist's notation, with the square brackets, you have the electrons that belong together grouped together. So this would be integral over Ij, and this would be the integral over the second electron in orbitals KL. Okay, so note the difference. If it was Dirac, then I would be with K and J would be with L. But in this notation, chemist notation, you group them with respect to the electron coordinate. Then it is immediately visible what's a Coulomb type integral and what's an exchange type integral, as you can see here on the lower part of the slide. Because if same index, you see this corresponds to something like a probability, which you can also interpret or understand in a classical picture, right? So this is just another way of writing things down. So we have the Dirac notation, then we have the chemist notation with these square brackets, and then we have also parenthesis notation sometimes, which is the same notation as the chemist notation, but only referring to spatial orbitals. So if it's written like this, it means spin has already been integrated out, and this is only about the spatial part of the wave function. This is just for you to know, because you might see different notations here. We will stick most of the time to the Dirac notation. Okay, so now this was all just like vocabulary so that we can use a different way of writing for our expressions. You could see already for the two-electron system, it was a little bit laborious to write down all these products. So this will be much simpler in this notation that we have just introduced. How does now the energy look like for our determinant? So we are in this n-electron state, and the corresponding total electronic wave function is psi naught, and the expectation value of the Hamiltonian is giving us the energy. And so we have these two contributions. One of them would be which we called the one electron operator, or a single electron operator, with this core Hamiltonian, sum over all occupied orbitals, AHA, for A going from 1 to n if we have n electrons. And then we have this compressed notation, which has this direct and the crossing terms packed together, Austausch and direct Coulomb and or exchange and Coulomb. So here I would have to, this one is just, we have this factor 1/2 to correct for double summation, because it's not about sums of electrons from A equal 1 to n and B equals from 1 to n, because then we would have a double summation, because it's only about pairs of electrons. So A with B, A with C, A with D, and so on. And then I take B, and BA is already covered. So I losing half. I don't need 1/2 of the term, so therefore 1/2 if I do the full sum. Okay, right, and this would be the way of writing it in this chemist notation. So far, this is all just giving names to things.
About what we now wrote down, this core electron contribution here, this little h, does this now encompass all the different Hamiltonians, H1, H2, together? Because this looks now at the first term like only for H1.
Yeah.
Case.
Yeah. Now this operator that is hiding behind this H is really just the sum over all the Coulomb interactions of a single electron with the nuclei and the kinetic energy term. But it changes, so to speak, when it's the for each electron we are addressing, because the operator index has to be the same as the electron that we are addressing, right? That's all. So it's just one operator. That's the same for all the electrons. It just has a different index because it's referring to first, second, third, and so on electron. But it's not a sum of core Hamiltonians.
Okay, then in this case, the sum that we are doing here over A, is this the sum that we had before by the single electron operator, where we had 1 and 2 bracket by
exactly.
this?
That's the sum, yes. Because
but then I'm wondering if this is the sum that we are having here, then shouldn't be for the 2 electron K, for the 2 H2, 2 of these sums there.
This is a double sum here. This means 2 sums because it's written with 2 indices.
Not this one, the core electron.
Oh, okay. You assume that yeah.
So that we have one sum for H1 and another sum for H2. Also we have 2 core electron Hamiltonians, except for example for H2.
Yeah. No, so there will be one sum as it's written here, but the core Hamiltonian here also contains the interactions of this single electron with all the nuclei.
Yeah, no, I got that. But if you could go back to the original form of the Hamiltonian that we had, there we had not a bit farther, not this one. I see this, but the total Hamiltonian that is written here, it has an H1 and an H2, and then on the next slide
Mm-hmm.
A step further. Yeah, we have in that term in the third line from below, we have these two terms, and I assume these are the two terms that are
No, but
written.
see, this is 1/2, 1/2. These terms are identical. So for each is just one term coming in. So this, what's written here, translates for an n electron wave function into a simple sum over A equal 1 to n, and then AHA in this bracket notation.
So the one here only refers to the electron and not to the orbital that we are looking at?
It refers to, so you don't have to, this is, since it is just one index here in this bra vector here, right? It's obviously just one electron integral. It's so D, we call it, let's give it a number, it's the first electron, right? And here, this first electron, and the only electron that we're integrating over, is sitting in the first orbital. And here, we do another single electron integral, but now we assume the electron is sitting in the second orbital. Okay? And so,
Okay.
yeah, and if I have n of these electrons, then I would just take these n orbitals where the electrons are sitting and would have to evaluate this operator for each of these orbitals. Okay?
Yes, then we have the sum here, but this seems only for one of these operators, only for one of the core Hamiltonians. But I do this procedure and I get these summands here, yeah?
Yes.
But I did it only for one of these H's.
Okay, I think what confuses you is this is for one H, but here O1, the actual operator as it appears in the Hamiltonian, is a sum. It is a sum of H A from A going from 1 to n. Okay?
Okay.
See, because here we just had two electrons, therefore it's just these two, H1 and H2. But if I have n, then it would be a sum over single electron operators, all of them separate core Hamiltonians.
Okay.
And so in general, it would be a sum. In this case, it's also a sum, but only with two terms because it's just two electrons.
Okay, yeah. I think I see the problem before from the third line. We have this factor 1/2, and then the
this
last line that it's away because already it is summed over all the core Hamiltonians.
Yeah.
I assume.
So for each core Hamiltonian, you only get one term. And see here, I've written that this looks would be the same. So if I just do it now for the first electron and for the second electron, I'll sum up and get different values because the orbitals will be different. But if I have n electrons, I have only n of these orbitals. And so I'm getting these single electron integrals, one for each of the orbitals, sum over them. And this would be my expectation value if my Hamiltonian consisted only of core or single electron operators, which it doesn't because it also has this O2, this 1 over R12, and this one introduces more terms because we have this coupling. If I just have two electrons, it will just give rise to one pair interaction, which is either a Coulomb or an exchange type interaction, right? And so if I have more electrons, this term is kind of exploding because it is a product term, a double sum, but since it's pairs, I'm introducing this 1/2 because otherwise it would have a double counting if I just do the double sum expression. Okay, I know it's a little bit confusing and you will have time to think about this through later again. Let me move now on to the actual process of the Hartree-Fock method. And as you said already, which was nice and to correct, if we do an optimization with a constraint, we can do it with Lagrange multipliers. And so what we have as our constraint is we would like to have the molecular orbitals at all time fulfill the constraint that the product of A and B, when integrated over the electron coordinate, is giving us delta AB, meaning that it should remain an orthonormal set of orbitals in all our steps. So this is our constraint, and what we do now is we add this constraint through Lagrangian multipliers as an expression to our energy expression, which we are about to minimize, and obtain the Lagrangian function here. Right, so this is now our Lagrangian, and this Lagrangian is now to be minimized as we would do it without these constraints by, for example, taking the derivative of the Lagrangian with respect to parameters of our test function, in our case, our set of orbitals that we are going to vary now, such as, or in such a way that we obtain the minimum energy distribution, or minimize the Lagrangian, so getting the minimum energy expression under the constraint of still having orthonormal orbitals. Okay, so this is the problem at hand. This is the Lagrangian. Now we know, because we just went through it together on the previous slide, how does the expectation value of the electronic energy look like for a Slater determinant from left and right hitting our Hamiltonian. We had these single electron contributions, and we had these 2 electron contributions with the direct and the crossover terms. So this goes into this first part of our Lagrangian. Then comes the constraint, and the whole thing now has to be minimized. And here I'm following this way of how Sauer and Ostlund are doing it. It's a little different approach in German textbooks, maybe because I don't know it has historical reasons that in the German literature it's very often explicitly worked through in this picture of taking the derivative with respect to some coefficients and so on. And this is how you could work your way through to get this final set of equations. An alternative, which is more common in the English-speaking world, is to look at it through a variational expression, put this variational expression into the equation, and then work from there. So I don't write the differential quotient and set it to 0 as you would do it in German textbooks. I just say we look at the variation in the Lagrangian and request that this variation should be 0, because then we know that we're at the stationary point of this function as a function of the parameters. So we can work with this even without specifying which parameters we're actually tweaking to change our test function, right? So I'm just saying I am introducing a little change in the Lagrangian. So we have infinite variation to the spin orbitals. That is simply a translation from our Ka into Ka plus some variation. And so I'm writing this arbitrary variation in a different delta symbol because it is supposed to be an arbitrary variation. And so we do this now and look at the parts. We have a variation in the energy, and we have this variation on, and here, this is again, it doesn't matter because in chemistry or Dirac notation, it would be the same, the product of A and B. Okay, so how does this now look like? First, let's evaluate this variation of the energy. So we just had discussed we just looked at the energy expression when evaluating Hamiltonian from left and right for a single determinant. This is now varied. So first we have the core Hamiltonian terms. Variation can be on the in the wave function on the left or wave function on the right. So this gives us 2 terms. It's like what you know from it is basically the product rule of taking derivatives, right, that we are applying here. Okay, and the same thing I'm doing now for the 2-electron integrals. And so this variation can be on the left-hand side on the place for first electron or at the place for the second electron. And then it could be on the side, on the right-hand side, variation in the first or in the second electron. The same thing also for the crossover terms. So this is what we get. And now, fortunately, we can simplify this expression a little bit because we remember, and here just not to confuse you, but you see this is in this square brackets notation here, right? So we are following this chemist notation. Here, this thing is the chi's are grouped together with respect to the electron coordinate we are actually integrating over, right? So remember, this would be chi A meeting chi A and chi B meeting chi B. So it's not like in Dirac where this would be with this and this would be with this. It's this two together and this two together in this chemist notation. So this is probably a bit more convenient to immediately identify what's similar and what's different. We remember, okay, obviously in the integral over one electron, it doesn't matter how the product is arranged, right? So ij equals to ji. So we can we realize, that we can put these together. So this term is identical to this term, and these two terms are identical, and so on, right? So this simplifies this quite a bit because this is just the product of the varied function with itself, and same thing here, varied function with itself as a product, right? So we can collect them. So it's just 4 terms, and there is another thing we note when we apply this infinitesimal variation, because if we take the complex conjugate, ijkl is equal to jilk and then in brackets star, we realize that the actual variation of our energy is simply an expression for the co-Hamiltonian that looks like this with the variation on one side, plus then variation on the left like this, and the whole thing that I've just written here again, but it's complex conjugate. Okay, so by sorting the terms and realizing that we can rearrange, we see that our variation has this expression and its complex conjugate. And whenever you have this symmetry in your set, this simplifies it by a factor of 2, because you only have to worry now for one of these terms. So we only have to make sure that this is also true for the second part of the Lagrangian, because this was just a variation in the energy, but we also have a variation in the Lagrangian multiplier, remember, because this is our Lagrangian. So now we just talked about the variation in the energy, and now we also have to think about what's going on here, but this is quickly done. So it's either varied on the left or varied on the right-hand side of this product. And so I can also write this explicitly as a sum over these terms plus a sum over these terms, and then I can rename A and B and see that this is basically exactly the same but the complex conjugate of the first expression. So with this realization, I see that our variation in the Lagrangian looks like this. It is simply an expression delta variation in the orbital or in the orbital A, h chi A, so these single electron contributions here, plus then these mixed terms. Then comes the term that stems from the Lagrangian multiplier, and then the whole thing again, but complex conjugate. And now we are almost at the end, and you will see this boils down even further. We introduce now, just to make it a little bit more appetizing and easier to remember, we define 2 operators. We define this operator here has the so-called Coulomb operator. Look what's going on. If this is, so I just want to find expressions that replace these types of integrals here. Remember, this is a 2-electron integral, so there's this 1 over r 1,2 operator hidden inside here. And so I will just give them names and call this the Coulomb and the exchange operator, going as follows. If this operator acts on orbital A, so this is a single electron operator acting on the electron 1, which is sitting in orbital A. And our Coulomb operator also has an index here. It's in this case a B. So it is the Coulomb operator that describes the interaction of an electron in orbital B with our electron in orbital A. And so when this operator is acting on orbital A, it is simply, and now you see that it's an integral over the second electron coordinate. From the left, we are coming with the orbital B, then 1 over r12, and same orbital B again. So this is simply what remains basically after this variation or this taking of the derivative, what remains of our Coulomb energy expression. You can see here, this is a direct because B and B star here, this is simply chi B squared. So this is the interaction of an electron density described by the electron sitting in orbital B with our electron in orbital A. Okay, so I'm just introducing this as an operator by itself. And I can do the same thing for the other term, which I call the exchange operator. So if the exchange operator acts on orbital A, it does exactly the same thing as the Coulomb operator. It is this integral over the second electron coordinate. But there is another thing implemented here, namely what we did before, the permutation of electrons 1 and 2. So if this exchange operator is acting on orbital A, it is on the right hand side also swapping coordinates for electrons 1 and 2. So now if it's acting on orbital A, and this is the first, this is electron 1, it is acting on this electron 1 in orbital A, it is not just executing this integral of B 1 over r with B. No, it also exchanges the positions, and therefore the orbital A on which this operator is acting on is pulled into the integral. Okay, so it does the permutation and then the integration. So this is what we call the exchange operator. So here I'm just introducing names to rewrite this equation that we had before and the variation. They are called Coulomb and exchange because if I multiplied this also from the left with orbital A, coming from the left with orbital A, it would give me the Coulomb interaction energy. See, because if I come in from the left with another chi of A, this time chi A star, and integrate over the first electron coordinate, I will get the 2-electron Coulomb interaction, as we had it before.
The first one in the brackets, is it always coinciding with the second number? In that sense, is it always JB1 Xi A1?
Yes. Mm-hmm.
Okay.
It's because this just means that we would like to investigate the interaction of an electron in orbital B with an electron in orbital A. And so it's just that, so when you look what's happening here, when the operator acts on this wave function, it produces something. And what it produces is a wave function times, and this must be some scalar value. So it is the integration over the second electron coordinate. Here it is basically the electron in orbital B with itself in multiplication. So this is a real electron density. So it's the density distribution for the electron in orbital B with the electron in orbital A. But this is just a operator notation, which turns then into a real value if I multiply, for example, from the left with chi A again, because then I would introduce the second integral now over the first electron coordinate, and then it would be what we defined before as the Coulomb interaction energy. Okay? So I know this is a little confusing. It just makes sense to refer to these terms that appear here in this variation here, in these two electron integrals as operators themselves. And this is the Coulomb operator, we call it Coulomb operator, and this is the exchange operator. With this notation, we can rewrite this equation here for the variation in the Lagrangian.
One quick question.
Yes.
Would there be a difference if you just omitted the parentheses with the one for the operator? Because to me also it seems, the only part where the one appears is the R12. So maybe that's why you need the parentheses. Is that it? I thought about it while asking the question, because before I was wondering, why do you even need to specify?
So the parentheses here, they are just introduced in order to make clear what's the actual operator.
Oh, no, I was talking about the other ones before. Same slide, but same line even, but before the equal sign. The parentheses specifying the operator.
Here, yeah. Mm-hmm.
Yeah, but now I noticed that it shows up in the R.
Exactly, yes. Because somewhere it has to denote that this interaction is the one of electron 1 in B with the electron in orbital A, right? So the one goes into the index here because it has to define between which two electrons we are.
I did see it when asking the question.
Then, no, but this is still a good question because it's good to point this out. So thank you for that. So that explains the one here, right? So this would be the Coulomb operator for describing the contribution to the electronic interaction that stems from the interaction of just the electron in orbital B with the electron in orbital A. And so with these two definitions for Coulomb and exchange, we can write the variation of Lagrangian like this. I always have to, wait. Move this a little away because otherwise I don't see. Okay, so that's what remains. And here I have made one simplification. We have pulled out our variation. See, let me go back one more slide. The variation is in orbital A, chi A, here, and here, and here. And so I'm pulling this now out and write the integration explicitly. Then I see that I have my one electron contribution, which would be this variation delta chi A H and then chi A again. Then I have my newly introduced operators, the Coulomb operator JB and the exchange operator B. But note that I have to sum over all the electrons in my system, right? So because they're all interacting with the electron that I'm working with. And then I have what remains from my Lagrangian multiplier, which I introduced sum over B equals 1 to N over chi B times EBA. Plus complex conjugate, but now I'm done, because if I would like this to be a stationary point, because I'd like to find the minimum, so this has to be 0, and this expression, since it's this and its complex conjugate, is only 0 if the term in the brackets vanishes, because only then it is guaranteed to be 0 for any type of variation which I choose for my chi A here, right? So that was the idea of the arbitrary variation. It has to be fully arbitrary, otherwise it could also vanish by this being, for example, orthonormal to each other, the expression in the bracket and what's written here. But so for any variation in chi A, this has to be 0, only 0 if this term in the brackets is 0. So let's write this explicitly again here and just put the term that stemmed from our Lagrangian multiplier, a term, onto the other side. And now we identify this type of equation as a eigenvalue problem. And a eigenvalue problem in a slightly mixed form. So we can just write this expression here, the core Hamiltonian, and then Coulomb term and exchange operator. We can write this as our Fock operator F. And then what we have here is Fock operator acting on orbital A is giving us a linear combination of all the other orbitals. And so the last thing that we do is we choose a rotation of our set of orbitals in such a way that F is diagonal. So it's just a tiny last trick. This would be the eigenvalue problem to be solved, and I'm looking for even more specific set of orbitals which fulfills automatically also this condition, but is more convenient to handle. I'm just saying that we are solving the eigenvalue problem for the Fock operator. We're just looking for eigenfunctions of this Fock operator. And this set of functions or of orbitals that we obtain are called the canonical orbitals. And so we are now almost at the end, because I mean this is now the Fock, the set of Hartree-Fock equations, because Fock operator acting on orbital A is giving us this Lagrangian multiplier that we introduced times this orbital. And so this is something that we have to apply to all the orbitals, and we get our set of orbitals from which we can then build the n-electronic wave function. However, there's just one problem that remains, and which is an intrinsic, little bit unfortunate feature of the n-electron problem. It is that the Fock operator itself depends on the actual solution of this set of eigen equations. Why? Because, I'm always losing the mouse here, so okay. Because when looking at the Fock operator, inside of the Fock operator, see, this is the Fock operator as we have derived it. We have these Coulomb and exchange terms, and they denote the B equal 1 to n. So these are all the other orbitals. So in order to solve this eigenvalue problem and get the corresponding eigen vector, which is in this case the wave function for electron 1 sitting in orbital A, I need to know all the other orbitals already beforehand, because they will define this Coulomb and the exchange operator that appears in the Fock operator. This is a little unfortunate because I don't have them at the beginning. So the whole procedure is an iterative procedure. You start with a set of orbitals as an initial guess, and then you have to repeat or repeatedly solve this eigenvalue equation, this set of equations, so you get a new set of eigenfunctions. With this new set of eigenfunctions, you calculate new Fock operators, and then you solve this set of equations again. And you continue this in the hope that at some point your set of orbitals does no longer change. And when this is reached, you have reached self-consistency. This is why this procedure is called self-consistent field iteration. So a set of orbitals determines our Fock operator to start with, here denoted as not for the 0th round. We solve this problem and get a set of new orbitals. But with this new set of orbitals, we also have a new Fock operator, and so we restart this whole thing. So this is the idea, and this is what's computationally so expensive. But I think, time is almost over, and we should probably use this last few minutes to make things more clear.
Can I still ask one
Sure.
question? Is there a mathematical theorem that ensures that going about things this way actually makes you converge or reach this self-consistency? Or could it also be that by plugging the answer into the function f, you will never reach self-consistency?
So no, there is no guarantee. And in fact, if you have very bad starting values, you won't reach convergence at all. Or, there are so many things that can go wrong in this type of calculation. You can have a very bad guess, and then it takes a long time to converge. It might also be the case that it doesn't converge because it shows an oscillation at some point. And this whole algorithm gets lost or stuck, doesn't move forward anymore. And so there's a lot of trial and error on the numerical side to get this going. And then there is another problem because we are looking for a stationary part, a stationary point on the Lagrangian, right? Because we took, in principle, actually the derivative with parameters that we're offering this test function. We're changing the orbitals somehow. Here we haven't discussed yet how we're actually changing the orbitals. And this is going to be a question which I'm asking you in 1 minute. So that's what's going on. It's a stationary point that we're looking for. That means that the first derivative is 0 with respect to the parameters which would vary. But it doesn't mean that this is a minimum. Yeah. And there are situations where it's a saddle point, for example, on the surface. So it is a little bit of a tricky problem, and most of the programs that I'm telling you all of this, it sounds very complicated, and it will take some time for you to digest or to fully understand it. In fact, on the computer, you just write HF. You give a molecular structure, and then you write HF, and then it starts the Hartree-Fock calculation for you, basically, because it's all automatized. But you should know what's going on behind. And there are a lot of smaller tricks that are implemented, and there is still a lot of research going into this because, as it turns out, Hartree-Fock is still a fundamental approach where all the so-called post-Hartree-Fock methods are stacked up on. Most of these methods for better descriptions of electronic structure are based on Hartree-Fock as their orbitals to work with, because Hartree-Fock gives you a set of orbitals, and with this you can work and improve on that. So that's why it's such an important technique. But now let me come to this question. So how would you probably vary this test function Ka? So how would you vary the orbitals? What would be a good choice? What's your guess? How would you do it?
A good choice, or how you could do it just in principle?
Both is okay. So if you have an idea how to do it.
The first starting guess would be, okay, I'd look a bit on the actual molecule that I want to look at and think, okay, what are the most outer atomic orbitals in some sense of my atoms? And then I try to guess a linear combination with free choice of coefficients. And then I vary the coefficients. Would be my first idea doing this.
Yes, this is a very good approach, and it is basically, no, it's not just basically, it's actually exactly what is done. So you are suggesting to vary the molecular orbital Ka by having a linear combination of atomic orbitals and trying to find those sets of coefficients which lead to an orbital that is then providing minimum energy. So that's basically what's done in all these programs on the computer that are available right now. An alternative would have been to try to discretize, for example, the spatial part of the wave function on a grid. and solve these equations on a grid. And at the beginning, people thought that it would be the better idea, but it turns out that the method, as you suggested, through linear combinations of atomic orbitals, has a big advantage, because when I don't want to confuse you too much with this, and I have a specific lecture dedicated basically to these details. It's called Modeling of Molecular Systems. It's in the Wahlfach catalog, and you can pick it if you're interested in doing electronic structure theory on finite systems, meaning on molecular structures. But just to give you a slight outlook, these Hartree-Fock equations here, they are actually a sort of an integral differential equation, a set of integral differential equations, because the solutions for these equations are these orbitals, Ka, B, C, and so on, and they appear in the form of derivatives, because the Fock operator contains derivatives through the kinetic energy operator that remains in the single electron operator, but they also appear at the same time in the integrals, because our Coulomb and our exchange operators have this integral form, as we have introduced on page 128. See, because the orbitals are also coming in an integral form. And so this makes it mathematically so complicated, and the solution is to be done numerically. But if you introduce now a set of atomic orbitals, and you describe each molecular orbital as a linear combination, the funny thing is that this integral differential equation translates into an algebraic equation for your coefficients, right? So you discretize basically your orbitals, your molecular orbitals, in a basis of functions, which are atomic orbitals. And what you obtain is then a vector with entries telling you how to linearly combine these these basis functions, right? And so the big advantage when doing this is that a lot of the iterative procedure that I've been talking here on this slide, the biggest part of this iterative procedure needs to be done only once, because you do it only for the basis functions, and then you can, so all these integrals you evaluate only for the basis functions, and then what changes is only the coefficients that form the molecular orbitals. And this was the great breakthrough that made these theories like 50 years ago to really catch on and be so productive and create so much new insights in molecular physics, because it was all of a sudden possible to work with many electron systems and get reasonable results, because this linear combination led to this simplification. You do it once for your basis set, and then in the SCF procedure, the only thing that continuously changes are the coefficients in the linear combination, and you don't have to do the integrals again and again. Another problem back then was that you have a lot of these integrals in the first place, so they had to think about how to store them on the disk and so on. But this was early days when computers were as big as a house, and people used punch cards, to program these machines. But this went basically hand in hand with computer development, and it has reached now a status where it is touching other fields, not just chemistry, but already pharmaceutical industries for decades now, and also now it starts to go into biology, because the systems that can be handled with electronic structure theory are getting bigger and bigger, because computational power is also increasing. Okay, so we are at the end. One thing that's missing, are we exact? Okay, so this is the challenging question. Do you think, are we exact here if we do Hartree-Fock? What could be missing?
Probably not, because it's still a variation approach. So there could be more parameters we could vary, for example.
Yes. But remember also, a variational approach can be exact if you are lucky and pick a test function that is already covering or is able to be modified in such a way that it becomes the exact solution, right? If there are examples for that. So, but you're right in the sense that we will be using, if we do this translation into a linear set of equations, we introduce a basis, and this basis will always be finite, and therefore it's always incomplete. But we can say, okay, I can go to a really, really large basis. This would be the so-called Hartree-Fock limit. And even the Hartree-Fock limit is not the exact solution. What could be still missing? What's your guess? What's not covered here?
Exact on what level? I mean, we're doing Born-Oppenheimer obviously here.
Okay, this is true.
But this we do not mean here.
Yes.
It's not exact.
But it's still a fair point. So for sure, there is also coupling to nuclear movement, and therefore this is a certain inaccuracy that we might rule out in cases we discussed, right? If this is sufficiently far apart in terms of energy, but it is an approximation that we've introduced. Yes. Okay. Is there anything else that you can think of that's for sure missing? If you look at the Hamiltonian, did we cover all interactions?
Magnetic interaction?
Yeah, which one did we cover? Only
Coulomb.
Right. So only a Coulomb interaction. So we only have interactions between charges, right? So the next thing would be in a multipole expansion to go to dipole interactions in the electromagnetic field. The next thing that comes up would be therefore the coupling of angular momenta, which correspond to a magnetic dipole moment, right? So that would be spin-orbit coupling and so on. But this can be put on top and then solved perturbatively, because this is a comparably small energy correction. But there is also an intrinsic error to Hartree-Fock, and this is my last thing I'm going to show you here. Hartree-Fock is a mean field theory. And so what we obtain here when you look at the structure of this set of equations is the following. We look for the solution for a single electron in orbital A with a Fock operator, which is an effective one electron operator. So what does it mean, effective one electron operator? It's effective in the sense that it is kind of emulating the presence of all the other electrons in this integral fashion, because we integrate over electron distributions that's stemming from electrons in other orbitals. But due to this integrative or integration approach that we are doing here, it is a mean field approximation in the sense that we are taking the average. We take one electron out of the system, look at this electron in the field of all the other electrons and in the field of the nuclei. And so just to give you a trivial example, look at these two situations here. If we stick with Hartree-Fock, which one has lower energy or higher energy? What would you say?
I mean, if we really do it in that sense that we exclude the other ones, I mean, the higher energy I would think was the right one, because we have the electron repulsion then.
So, I mean, it's a little misleading to bring it this way because we are not dealing with point charges in the first place, right? But what I'm trying to make clear to you is the following. What Hartree-Fock does is the following. I'm taking, for example, electron at position R1. And now I would like to know the energy of this electron in the field of all the other electrons and the nucleus. So let's assume the other electron is in an s orbital, okay? So it's spherically symmetric and has this S-shaped distribution. And so you're taking the average interaction of this electron at position R1 with this distributed electron. And so here, it doesn't matter where electron R2 is actually located, right? Because you will have to look at the average distribution in this kind of static picture of the orbital with a certain given electron density distribution. But in fact, this is a dynamic process still, and we haven't covered this dynamics, because if an electron has a tendency to be more often somewhere in space, it makes sense for the other electron to be less often at this point in space, right? So in the real molecule, the motion of the electrons is correlated dynamically, they are interacting. So if some electron is more often at some place, then the other one is less. And this time aspect, this is averaged out here and is therefore missing, okay? So this is what we call the correlation energy. And by definition, Hartree-Fock theory gives you 0% of the correlation energy. And so you're putting additional types of calculation on top of Hartree-Fock to account for this missing correlation energy. So that would be the so-called post-Hartree-Fock methods. For example, maybe you've heard of this coupled cluster approach, or density functional theory has ways of introducing also correlation energy. So this is what goes then beyond Hartree-Fock and is giving you some percentage. And if you have 100% correlation energy, then you have reached the exact solution for this problem, for the n-electron problem, in the non-relativistic picture. So without other interactions coming in, such as also the spin-orbit coupling interaction, which can be interpreted as an effect stemming from a relativistic point of view. But I will probably cover this in another lecture. Okay, so that's it from my side. I ask you to quickly grab your phone and enter feedback. Today's code is CHFKD. CHFKD. And we have, as usual, 3 questions. First one, what happens to the total electron wave function if we swap 2 lines in the Slater determinant? Question 2, which dependence enforces the Hartree-Fock method to be iterative? Here I give you the options, because for those who don't have the phone at hand, it's hard to anticipate. I have offered the following answers: the dependence of the Fock operator on the molecular orbitals, the dependence of the effective Hamiltonian on the eigenfunctions we obtain, 3, the dependence of the nuclear geometry on the electronic energy, and 4, the Hartree-Fock equations are not iterative. And last question, do the Lagrangian multipliers which we have introduced have a physical meaning? This is more like a guess for you now, because I didn't mention it, but it's actually an important thing, so I will take my time to go into details next time, but maybe you can anticipate it already. So, okay, I think, yeah, we have almost the same numbers on all questions. I'll probably get going with the first question. What happens to the total electron wave function if we swap 2 lines? The correct answer is it picks up a sign. So let me stop. Yes, 100% did get this correct answer. Then, second one, which dependence enforces the HF method to be iterative? And it's one of the nasty questions where 2 answers are correct. The first 2 are correct. The dependence of the Fock operator on the molecular orbitals we calculate. And it's the same thing to say this way, the dependence of the effective Hamiltonian on the eigenfunctions we obtain, right? So this effective term that we derived actually from the Hamiltonian, I have to say. Yeah. Okay, so this is the second, and the third one. Do the Lagrangian multipliers we introduced have a physical meaning? And I am surprised. This is a very good result. 80% voted for yes. The ith multiplier corresponds to the energy of a single electron in the orbital. It is sort of obvious if you look at the equations that we all ended up here. It's the eigenfunction. This is the eigenfunction, and the corresponding eigenvalue has the unit of an energy. And it turns out that this energy has a physical meaning because it describes the energy of an electron when sitting in this orbital. So this is another thing that we can use in Hartree-Fock. If we have solved and we have our set of orbitals, then we can also estimate the ionization energy, because I'm just filling up now my system with electrons, taking the n lowest energy orbitals, using them, filling them up, and the highest occupied molecular orbital has then some energy. And if I look at this energy, I can directly read how much it would cost to remove this electron from the system and turn my molecule into an ion, right? So this is the ionization energy. And similar things can be said about what happens when you add an electron to the system, but I'll talk a bit about this probably in the next unit. Okay, so I also have to stop now. Thank you all for your attention. I'm going to switch off the recording now.